So you said just put a magnet underneath. You're right. I mean, a magnet or an electromagnet or something. So this is a nice picture, I think, that shows how this works. So you have, let's say, a silicon substrate, your GMR film here. This is your GMR film here. And you have a magnetic bead. Now, when you have an electromagnet, let's say it's applying a magnetic field this way, okay, then this bead will have a magnetic dipole like this, right? So it will have a stray field. Now, the GMR sensing element actually measures that.
Change it. It's the magnet.
Yes, it's that it is that stray field when it's magnetized. That's what the GMR sensor measures. Now, with this one, I wanted to kind of talk a little bit about some of the limitations. So, I mean, so far, I think I've been explaining like everything's perfect, right? But even, like with the hard drives, there are some limitations of this method. Now, so I think here, yeah, I think the students can probably understand this. I'm not sure if they. So basically, this is a standard equation that you can get from any kind of electromagnetics book. Now, this is a magnetic field. Let's say you have a dipole moment here, and if you want to calculate the magnetic field in this direction, let's say your x direction, right? You will have an equation like this, right? This can be taken directly from a electromagnetic textbook. But here the thing is, few things I want the students to understand. One is that, so here, what do we know? M is the magnetic moment,
Yeah,
right? And that's equal to the magnetization times V. V is what? Is the volume of the bead. Okay, so if you look at this picture here, okay, this is the bead here. This is your sensor. But remember, between your sensor and the bead, there is this passivation layer.
So there is a gap.
There's a gap. There's always a gap to protect the sensor from all these fluids. And that has a certain thickness T. Now, here we are talking about the magnetization. We are talking about the magnetization of the, not of this. We're talking about the bead.
Yeah.
Right? So then the volume is the volume of the bead.
Correct.
Right? So in this case, it's a sphere. So it's 4/3 pi r cube. But r in this case is a.
Yeah.
Okay. So a cube. Okay. We know that. Now if you look at z here, what's z?
Z is the radius plus passivation layer.
A plus T. And then R is here.
That's the root. I mean, sum of the root. I mean, square of the root.
Yes. So it's square root of z squared.
Yes.
Plus t squared.
Yes.
Okay. Now, if you, okay, so that's fine. Z is this, D is this. Okay. Z we know this one. Okay. So then, if you insert this to the equation above, you have mu0 divided by 4. Okay. 3 times 4/3 pi a cube. Correct? A plus T, which is Z, times D. Cut. And then 4 gone. Pi is also gone. Sorry. Yes. Then below we have r to the power of 5. So this is same as z squared plus d squared to the half, right? So then we have r is A plus T squared, which is Z squared.
Yeah.
Plus D squared, half times 5, 5 over 2. Right? And that's how you get this equation. But looking at this equation, Bobby, what are some of the things that you can deduce?
A cube.
So now we are looking at the magnetic field in this direction.
Yeah.
Okay? A cube is this one. Yeah, where A cube is the, yeah.
So that is something proportional to the volume.
Yes. So ideally,
That you cannot change much.
yes, that you cannot change much. And when you talk about the magnetic beads, a bigger particle necessarily doesn't give you a larger magnetic moment, because it depends on how much. You could have a small amount of magnetic beads covered with a large
Number of.
coating, right? So that doesn't necessarily mean that it's going to give you a higher. So that's again hard to control.
Okay.
But what for sure we can control.
D.
Yes. So that also means how far away is this bead from the magnetic field center. Yes, center. And the thickness. Again, T squared and 5 over 2. So that thickness also play a key role. But when we are designing something like this, we have full control over the thickness. So if you can go low as possible, it's good. But maybe then that means you might not be able to use that over and over again. If you clean it, the layer might just come off.
Vanish.
Yes, vanish. Exactly. So you made a very good point about the center. What do you think happens here with the center? If you look at the magnetization, if you look at the stray fields.
No field.
Yeah, very low field.
Yes.
Yeah. So that's one of the disadvantages of this system, is that you get a very, very small field. So in fact, you'll most probably see the peaks on either side, right?
Yeah.
Something like this. So, which means it is hard to detect if you have multiple magnetic beads. Now, there's another disadvantage, or limitation rather. Let's say you have the chip. Now you said, can we use a magnet? Yes. Can we use electromagnet? Yes. And then in a situation like that, we'll have a bio chip here. We'll have electromagnet or magnet below it, right? And then you'll give either a DC power supply or a AC power supply to the GMR bio chip. And then you analyze the output by means of a lock-in amplifier. If you use a
Exit. Yes.
but then you can use a lock-in amplifier. For that, you can use a function generator to give the same reference of the same frequency that you use here, can be used to detect the magnetic flux density, and then the computer. But what is the point of making things very small when you have this huge electromagnet or magnet outside?
Right, that is true.
What's the point? So there's another limitation, because if you want to make things smaller, you want the whole system to be small, right? You don't want to make it small and then add another component that is huge. So these are some of the limitations of this kind of system. So next we're going to talk about how some of the things we can do to improve this system and this setup.
The biomedical application?
Yes, biomedical application. But just as with the hard disk, how we went from longitudinal to vertical, for this also we have some things we can do to get rid of this large electromagnet.
Oh, nice.